Okay, good morning everyone. So welcome back to this class. So last week we have already introduced some of the basic introduction why we need to learn the semiconductor and what you can expect to learn from these courses, including the basics and some of the advanced technology and also some of the emerging trend for the future application. Therefore that's why we still need to put a lot of effort to try to make sure that our semiconductor technology can enable those emerging application. So we have been go through some of the basic from the early high-K metal gate until the so far the FinFET, which is one of the key and the critical technology enable the semiconductor down to the 3 nanometer and 2 nanometer, and for sure we have getting more and more innovations that we need to further explore for the future technology nodes. So what we have been discussed last week, this is a typical structure for the FinFET, which has this kind of the three-dimensional gate that wrap around our source and drain region, where is our mainly the current will be flow from this to electron will mainly flow from the electron to the drain. But now in the past, if we talk about the planar, we can only control the electron flow from the top surface, but nowadays we have this three-dimensional structure that help us to control the channel not only from the top surface but also in the side wall, and therefore we get a better electrostatic control. In the end, we can achieve the better on-off ratio and better substantial swing. So as you can see from the typical IDVG characteristic, that's the first demonstration in the 1999, which is fabricated for the PMOS. That's already demonstrated as 69 millivolt per decade for substantial sweep, and also the on-off ratio is relative good because the on ratio is around like the 8 order from the 10 to minus 12 for the off current, and also the on current can be reached to around beyond the 10 to minus 4. So that's a very good demonstration for the FinFET technologies. And of course, so what we are going to do for the future, we still need a lot of effort to explore the options beyond FinFET. As you see from this slide, there are so many novel structure, novel device, and also based on the novel material, novel mechanism that can be the certain options beyond the FinFET. So we can divide by the conventional structure. So conventional structure will be still based on the typical MOSFET mechanism, typical MOSFET operation, but just a variance, just a difference, a little bit novelty based on the conventional. But also we have something else that's a novel mechanism that's completely use some of the physical mechanism that we have never explored or we haven't been commercialized yet, but that shows a very promising, and also can be divided by the charge and non-charge base for the device operations. So first of all, for sure, based on the conventional, even the conventional device operation mechanism, we still can have many innovations that help us to have certain novelties beyond the FinFET. For example, for the conventional, what we mean here is mainly for the scaling. So we still work on the CMOS scaling, and that's also including the better electrostatic control. We want to have the better driving. That means we have the higher on current based on the CMOS scaling, and also we want to minimize the parasitics. As you know, that we try to make the transistor device as smaller, and we have getting more and more transistor put together, there are always a lot of the parasites that will influence our device performance. So in the end, we always want to minimize these parasites. That's including the capacitance, that's including the inductance here. So one of the most well-known so far is getting almost ready for the production, will be the target for production for the next 2 to 5 years, which is definitely the gate-all-around narrow wire. So the gate-all-around narrow wire has been already considered as something that beyond the FinFET, but we can also divide by the different architecture for the gate-all-around, which is first could be the horizontal gate-all-around and also the vertical gate-all-around. So that's something that has been people in the industry and academic has been working very hard trying to make this as a commercial products. And also we have something else, for example, the free deplete SOI. That's where we already mentioned that's already the one options that we put as an insulator on the substrate to avoid leak current from the substrate. And also consider the 3-5 and germanium. That's something we need to improve the channel mobility. And also we have a carbon nanotube FET. That's also something people put a very promising. People consider as a promising technology for the next 10 years. But unfortunately for CNT FET, carbon nanotube FET is still very difficult to have the mass production, because you imagine you have to grow. What we are working in the industry is not only to fabricate the one golden device, but we need to fabricate a device that has a good uniformity along the whole sample, whole wafer, which is up to the 300 millimeter. We need to make sure, we need to guarantee for have the 90%, 95% yield, and also we need to guarantee for good reliability. So that's still lots of the challenge before the successful manufacturing and productions. And for being the academics in the university, for sure we will keep in looking for some options. We won't want to miss any options. So there's getting more and more novelty that we are coming out in the past decade, try to have some options beyond the FinFET. So this is something where we have the novel mechanism. For example, one of the famous one, which is what we call the tunneling FET. So in the case with the tunneling FET, we mainly leverage the tunneling mechanism. And what is the tunneling mechanism? Where we have been already brief mentioned last week, is based on the quantum mechanics. So once you have quantum mechanics, you always have a tunneling mechanism. So tunneling is something that we cannot avoid when we work on something in the very, very small scale, especially in the micrometer, in the nanometer. And therefore, people consider to turn this quantum mechanism, quantum tunneling, as a one operation mechanism for the field effect transistors. That's what we call the tunneling FET here. Also, another very promising, like in the last 10 years, what we call the negative capacitance FET. Negative capacitance FET here. The negative capacitance FET is based on the innovation that where we have this ferroelectric material. So because of ferroelectric material, we can start to see the capacitance might be switching to the certain area that has a negative capacitance. And once we have the negative capacitance, that we can see the voltage amplify. And then once we see the voltage amplify, we can see this can boost our on current and also minimize our substrate swing. So that's also very promising direction in the last 10 years. That's we call the negative capacitance FET here. Of course, the physics for the negative capacitance still under the debate. Some people believe it, some people didn't believe it. But in the case of the demonstration performance, it's indeed possible to have the sub 60 millivolt per decade switching and also have the on current driving. And also another very promising is a 2D materials. That's also, I believe that some of you in the class also work on the 2D material. That we feel like the 2D material can be the option for the certain beyond the FinFET as well. So these are the transistor, are the field effect transistors that are all based on the novel mechanisms, and these are the knowledge and then the experience that has been accumulated in the last decade. This is not the technology that we just developed in the last 5 years. All this has been thousands of the researcher engineer has been explore, has tried to be understand, has tried to development. So for sure that in this class we won't be able to talk everything, because everything, one of these topic can be the certain knowledge beyond the one PhD. So you won't even able to try to familiar with a one PhD. It's considered as a accumulation of knowledge in the last decade. But it's good for you to understand that there are many innovations that are beyond what we have so far, and that every of these topics are very interesting, very promising, and that all of them are very good for the future of research. And also, there's something that are beyond what we have been talking about is a charge base. We still consider the carrier, the electrons and holes accumulation in the channel and switch on and off. That's what we call the charge base switching. But certainly there's something beyond the charge base switching, and this will be dramatically different from the CMOS logic. So the good thing is that we don't leverage any charge anymore. So we don't consider the charge accumulation and turn on and turn off. But the challenge will be that even if this can make it as a commercial product, we still need to have the innovation for the circuit design, because all these operations are completely different as a typical CMOS, and therefore even for circuit design, in the system design, in the circuit and system operation, we also need a lots of effort to design. So that's why you will see, like in this case, the quantum computing, which is very promising. But to be able to realize the quantum computing, you need to have a quantum circuit. The concept for the quantum circuit is completely different from our typical digital and analog circuit, where you have learned from the basic electronics. So that would be another domain you have to really further explore and then try to establish the solid design for the quantum circuit. But it's a very promising for sure that the quantum computing can be the technology in the next decade. But how long, we don't know, but it's always as a key technology. And also we have this all spin logic, the FinFET spin logic, that's based on the magnetic material. So once we have a magnetic material, we are able to see this magnetic switching. That's all possible as a spin logic or spin field effect transistor. But as I say, this also leverages that we need to have develop the novel circuit, novel system, try to use this technology. So no matter what kind of the technology we are working on for the beyond the FinFET, or what the FinFET we are working on, or what the nanowire we are working on, the general goal for the CMOS logic, the general goal for the advanced technology, why we have to do the scaling, why we have to keep pushing the high current, the general goal is we want to have this low power consumption. Because once we have a low power, that can save energy, our computer, our laptop can run longer. our cell phone can run longer, and then also our data center can have more and more GPU, and that's also good. So we need to have a low power consumption. But how do we realize the transistors are able for the low power consumption? So here is the key why we have to keep moving towards the scaling, towards some advanced technology. And then how do we understand the low power consumption? We also have to starting from the typical characteristic, where is IDVG characteristic. And then right now what I'm going to plot is a logarithmic ID versus the gate voltage. As I already said in the first class, that the IDVG is one of the key electrical characteristic we were first to sort out in our mind. Whenever what kind of your device you are working on, always keep in mind that you have to first to look at their IDVG characteristic, because IDVG characteristic that already contains a lot of information. So imagine we have this IDVG characteristic where have this typical characteristic. So that's a typical IDVG where we have been shown. We have the off current here, we have on current here, we have the certain turn on period which we consider as a subthreshold region here. And how do we make it as a lower power? So when we talk about low power, that means that we define this point as our operation bias, where normally we consider as a VDD here. So if we want to have a lower power consumption, that means we should be able to reduce the drain bias. But at the meantime, we want to keep it as the same performance. So if we can have the transistor that keep as the same output current, but we want to have a transistor has a lower operation bias. So what would be this IDVG looks like? And therefore, this curve should be somehow become like in this way. We need to get a little bit steeper. We need to have a little steeper for the slope. That means if we can have a steeper slope, that we can have a lower drain current. Lower drain bias, lower drain bias, lower VDD here. So therefore, this can be our VDD plot. And furthermore, how we can further reduce power consumption. That's a goal to reduce the VDD. So therefore, if we can make it as a transistor, as an even slope, it's getting steeper here, just like here. We can start to see the VDD plot is getting smaller, and our target is try to make the VDD plot smaller than 0.5 volt here. So to be able to make the reduce the power here, reduce the operation voltage, reduce the power consumption from the transistor aspect, what we have to do here is try to make our transistor as a switching during the turn on period as a steeper as possible. This slope should be as steeper as possible. And then this slope is what we call as a substrate slope. SS. So that's why you can see, no matter from the TSMC paper, from the FinFET paper, there's always highlight their SS because they want to demonstrate their SS can be as a sloper, as a steeper as possible, because the implication for this steep slope means that we can have the lower operation voltage for our transistor. In the end, can make it as a low power consumption here. And of course, when we try to make this steeper, one of the another aspects that we want to save the energy, save our electricity, save our power. So when the transistor is in the off state, we should make sure that the off current should also be as smaller as possible. So this is the goal, that how we try to fabricate a transistor for the next generation, for the next 10 years. In the end, it's always we want to reduce I-off. We want to make the slope as steeper as possible, which means that we need to make the substrate slope as smaller as possible. If we can fulfill these two aspects, we can make it as a transistor target for the lower power consumption. So in the end, it's I hope this slide just help you to understand. It's not that difficult to understand the goal, because the goal is simple. We want to make the off current as smaller as possible. We want to make it steeper slope, where its SS should be as smaller as possible. That's why to realize this electrical goal, that's why we have so many innovation. We need to have a FinFET. We have a gate all around. We have something beyond. Okay, so the next one is also want to mention again that when we talk about the semiconductor technology, that would not be only limited to the MOMO, where we already mentioned that in the case of trying the transistor to have the scaling, which is based on this CMOS technology, that we want to make as a transistor as smaller as possible, 3 nanometer, 2 nanometer, and beyond. But on the other hand, there's another domain where we focus on the technology that interact with people and environment. And in this technology domain, we call as a more than more. And in this domain, there are many different options. We consider the BIOS chip, we consider the sensor, we consider the analog RF technology. That's all in the domain of the more than more. And in here, I use my expertise in the high voltage power as an example. So, for example, as you know, when we come to the AI area, that we need so many semiconductor technology innovation, and one of the challenges for the AI technologies that costs a lot of the power requiring the lots of the power to powering up our data center. So this is one of the example from the different kind of the NVIDIA GPU here. So we have this Hopper until the Grace, Blackwell, and then beyond. And then we have, this is already the information from 2024. So that's already have this 4 nanometers technology to enable for the Blackwell GB200 data center. But one of the things just want you to draw attention is that the power also is increased, getting more and more. So for high performance AI server like the B200 or GB200, a single GPU can consume more than 1,000 watts of power. But if we consider Blackwell has a 2,000 GPUs, so that means we need to make sure that we can deliver for 4 megawatt for the AI data center here. And in the end, that would be the more than 100 kW per rack. So in the end, this AI data center become as one of the monster for the power, because we need to make sure we need to deliver lots of energy, electricity to drive our data center. So, but this still in the GB200. But as you know now, the latest generation is not the GB200 anymore. We start to see the GB300. We start to see the getting more and more, and then we start to see the getting more and more GPUs in the one chip, and therefore we expected this will cause a huge energy demanding for the worldwide electricity. So how do we address these issues? One of these solution is we need to have this power conversions innovation. So here, this is one of the typical schematic that the power conversion unit for the AI data centers. So as you can see that this is our electricity coming from the grid, and normally when we come to this, that would be the AC voltage. So in Taiwan we have a 110 AC. In the other international country, usually we have 220 or 230 AC. And first of all, we need to have this AC to DC converter, and normally that's we call the PFC. And then later we have this LLC, where we start to convert the high voltage DC to the low voltage DC. So that's right now for the 48 volt or 52 volt. And later we still need this DC to DC in the end to convert to the voltage that we needed for the GPU. So normally for the GPU, what we needed is less than 1 volt. So now you see the electricity we provide for the GPU cannot be the direct voltage that we got it from the electricity grid, because the electricity grid where we get it is such high voltage AC. We need to have so many down converting from the high voltage AC to high voltage DC, high voltage DC to the medium DC, and then the medium DC to the low DC voltage. And then each power converting always pays some penalty, especially the efficiency is not perfect. The efficiency can be 80%, can be 90%. And therefore, many of the people is trying to improving the power converting efficiency, try to improve from 80%, 90% up to 95, 96, 97. That's why we need to start to have the new material, new semiconductor technology that help us. So this is one example. We can use a gallium nitride based technology. We can have the gallium nitride based technology to enable for more than 98% of the efficiency. And also in this region where we have the 48 volt to 1 volt, we can also use the gallium nitride to transform the energy from the high voltage to the medium to the low. But at the meantime, we can increase the efficiency. So that's one of the examples that how do we use semiconductor in the more than more technology. That's also try to address the power challenge. For the CMOS technology, what we are doing for low power consumption is also the same. We want to save energy. We want to reduce our operation bias. For the power device, for the more than more technology, when we tackle this high voltage conversion, we also try to address these power challenges. So therefore, you can see this is one of the startup that NVIDIA who already announced in the last year that the NVIDIA already worked with several different power electronics companies, try to work on the next generation of the power electronics for the AI data center. So this is one of the examples that try to have this 800 volt AI data center that can increase efficiency, save energy, that can meet the demanding coming from the NVIDIA data center. And then this is also the one example to give you as a general aspect that how the energy, electricity we can get it from in this classroom where we can charge it for your a laptop, cell phone is not coming from free. It's coming from the multiple power converting. We have the electrical grid that can provide us a high voltage AC, and then we have this first converting from the AC to DC. As I already said, we have to convert the electricity from AC to DC, and then we start to have this. This is already in the IT rack that's converting from the high voltage DC to the medium voltage DC, and in the end down to our GPU. So that's how actually the electricity infrastructure that we need the innovation for the data center, but us also need the novel semiconductor material that help us to make it. Of course, for the more and more technology, if we talk about the high voltage power, is not only required for the data center. Of course, for the electrical vehicle car, that's already on the news on the market for a long time, that how we can leverage this new compound semiconductor to enhance the performance and save energy for our EV car. So this is one example. So we can use this silicon carbide MOSFET inside as our EV car, which is mainly target for the traction inverter here. So the traction inverter is mainly trying to convert the DC to the AC, and then the AC can start to drive our car here. So we need to make sure that this converting give a lot of watts that can drive our EV car here. And here is just an example that the silicon carbide can increase for 3 to 8% high efficiency. So once we get a high efficiency, for sure that our EV car can drive longer and also can make us less time consuming for the charging. So overall, if you look at the semiconductor technology trend, that whatever we done for the advanced CMOS, we want to make it as low power consumption, or if you look at the demanding needs that we need to power our AI data center, we need to power our EV car. In the end, the goal is the same. We want to address the power challenges. So the power challenges will keep driving the semiconductor innovation for next generation, and then what we want is always energy efficient electronics, no matter coming from the aspect of advanced logic or coming from the aspect for the more than more. We always want to reduce the power consumption, make the efficiency, the converting efficiency, the delivery efficiency as higher as possible. So if we can increase 1% efficiency, that means in the original you need to build up 100 nuclear plants. But if you improve 1% efficiency, then you can only make it as a 99 nuclear plant. So if you put it in the large scale, you can see that how this dramatically impact on the Earth and our typical life. So we don't need such that nuclear plant, but we still can keep our alive to enjoy some of these amazing technologies. Okay, so then let's look at what would be the industry consider for the next generation. So this is the slide coming from the TSMC to look at from the early time, from 2010, where we already mentioned, from the planar to the FinFET and to the nano sheet, and what actually the innovation help us to make it from the 28 nanometer, where we have a high K metal gate, we have the high density MIN, strength silicon, we have the EUV, we have a high mobility channel, we start to have the FinFET and low K, and then the beyond. And then right now we have this what we call the power rail. So power rail is mainly in the past, we always think about that you have a substrate and then you make the transistor stacking higher, and then you always powering, you apply voltage from the top of your transistor. But now you're stacking so many layers, so then the transistor here, and then you try to apply voltage from top, the distance is way too long, the interconnections are way too longer. So therefore we turn into another way around. We try to powering our transistor from the bottom. So you need to have this through silicon via from the bottom, and then start to provide the transistor from the bottom. So that's what we call the backside power delivery. That's also considered as a power rail. That's some new technology that's being developed so far. So if you're still interesting to look at this is a slide coming from the 2024 from the very senior director from the TSMC who present this process technology evolutions. But if you back to the old slide, this is slide from 2019. That's already 5 years earlier than the previous TSMC roadmap. But still see the several key terms still similar. In the 2019, we still talk about the FinFET. We still talk about the nano sheet. We still talk about nano wire. We still talk about the 2D materials. So that means that what we are actually doing now probably is not in the industry roadmap, but it can be in the next 10 years, 20 years. And that's also similar since we have been seeing that all these successful products that needs decades research and development in then become the production. So many of the news or many of the general news will say that when we go for the graduate school, the graduate study doesn't make sense. What we are doing just to try to understand the paper, work on the paper, work on the academic. Might be true for another domain, but definitely it's not true for the semiconductor and then electrical engineering. What we are doing here is really critical because we believe what we're doing here after 5 years, after 10 years, is always will be target as a production. We will never work on some technology that never has the potential of becoming a product. What we are doing here will be always be variable for future technology. So here is one of the examples that in 2019, people talk about FinFET, nanosheet, nanowire. At the moment, this is what they call the development. You see, this is still under the R&D phase, and then people thinking nanosheet is interesting, but they never be able to production. But if you look at nowadays in the 2026, the nanosheet and nanowire is ready, almost getting to be production for the 2 nanometers. Okay, so here is another roadmap that look at beyond the FinFET. That's where the TSMC have been shown is up to the 2 nanometer, 1 nanometer. But if you look at the roadmap coming from the IMEC side, they make it a very nice prediction. So we have N3, which is the FinFET, and the N2, that's also the gate all around nanosheet, and then the A14. But most importantly is beyond the nanosheet, we have this fork sheet, we have this CFET, which will be the future for the continued dimensional scaling, as you see here. If you want to make it as a dimensional scaling, we need to make the metal pitch as a smaller, but we also need to have the device and materials innovation, and therefore we need to start to consider as a CFET. And then in the IMEC roadmap, the CFET will be considered as a production in the 2032. So what is actually the CFET, the difference between the CFET and then what we are doing now? So right now we have this PMOS and NMOS put together, so that's a triple gate FinFET. That's a triple gate FinFET. And then beyond FinFET, what the big giant semiconductor company working on is trying to have this gate all around. So this is a gate all around vertically stacked lateral nanosheet FET. And then beyond the gate all around, and then we have what we call the fork sheet FET. And also, then you see, even in the fork sheet, the PMOS and the NMOS are put to side by side together with the same planar. So what if we can make it as a PMOS and NMOS on top, vertically on top of each other? So that's we call the CFET, as you show me here. So in this structure is a NPMOS stack on top each other. That's we call the CFET. So nowadays, in the industry, we believe that CFET can be the advanced solutions beyond the fork chip, because now you see that we stacking the NFET on top of PFET, and the most important is we save the area. The area is getting smaller, and then the density can be increased. So once the density increase, that means we can put more and more transistor, and then more and more transistor means that we can get a higher performance of our chip. So that's idea for this CFET. So still try to look at how the industry leading advanced technology portfolio here. So we have this FinFET for the N3, all the advanced N3, but moving to the N2, we will have the narrow sheet. So this also provides us one aspect for everyone, that understanding the semiconductor device architecture, semiconductor physics, semiconductor device operation is getting more and more important. Because if you talk to the IC design house, if they want to design the very good nano chip, they must have somebody who understands the operation of the nano chip. Because nano chip from device architecture is already completely different as a typical planar FET, and also different for the FinFET. And also in the beyond, in future, they want to design the CFET. They also need the people like us who understand the CFET device architecture operation. So therefore, from this perspective, that understanding this knowledge, also the operation, semiconductor physics device, in the past, people feel like this is just a very basic courses, and then the value is good, but it's just not that getting important compared to the some other popular courses like the digital IC, analog IC. But now the things is changing because of you know how to design the DIC, you know how to design AIC, but if you don't know what is a nano sheet, what is a CFET, you cannot design. You don't know how to doing the best layout design. You don't know how to optimize the performance. So then, therefore, that's why we call the design technology called optimization. Because so if you want to produce the best chip, you need to optimize not only the circuit innovation, you also need to optimize the process, how we can make the process better to reduce the loss of non-ideal effect, and how do we design the transistor. All these things are tied together for the next generation of the chips. So this is also one example that why the NVIDIA, why the Qualcomm, why the Broadcom, why the Apple, why the Google, they all need advanced foundry, closely work with them, because if they cannot only survive with their novel design, because if there's no device people can work with them, teach them, their designs cannot be realized. Okay, so here is also the slide coming from the TSMC, try to explain that what would be the mainstream and then the high end. They divide the technology by the two different targeting product. When we talk about the mainstream, which means that, for example, the mobile phone, consumer, network, and then when we talk about the high-end product, that's also considered the premium mobile. That's mean, for example, the most advanced of the cell phone, data center, AI accelerator. That's they need this high end. So once we need to produce a high end product, we need to leverage the most advanced semiconductor technology. And here is also the slide. Just want to emphasize again that the technology what we are trying to develop for the future. That's actually already in the textbook, in the literature that has been discussed in the last decade. For example, the CFET, where we just shown, and also some of the very promising for the 2D that still need we still face a lot of challenges for the 2D. For example, the poor contact, the low on current, and then lots of the manufacturing challenges, lots of reliability challenges, but still considers a certain beyond the silicon. So this is the latest the TSMC result that this is coming from 2024, last 2 years ago idea that as we say that in the IMEC roadmap, the CFET is considered as a production in 2030, but it's already the timing that we still need to work on to see whether it's possible to realize the CFET. So that's the demonstration, the CFET silicon, and that's already shown the very good characteristic. And also, as I say, this is just also one example you see from the key result, key electrical result from the paper. We always talk about the IDVG characteristics. So in the 2024, they demonstrate the functional CFET, especially with a good substantial swim here. And now the operation voltage here is 0.9 volt. And of course, our target is try to make it less than 0.5 volt. So that's, I hope nowadays, at the moment, you can understand that how this IDVG curve implies for us. How do we interpret the low power consumption from this IDVG characteristic? And also, this is 2024. And then if you look at the 2025, that's the idea coming from last year. They also have this CFET demonstration. This is the first demonstration of the CFET. But now it's not only for the device level demonstration. They start to work on this ring oscillator, SRAM, and that's for the future logic and SRAM technology. And of course, in this paper, they demonstrate lots of the figures. But I just want to this is architecture where we already shown. This is a typical SRAM, where we won't talk about SRAM here, but just let you know this is typical planar. And the CFET, just we want to put the transistor staking on top of with each other. So now we have the NMOS and PMOS staking on top of each other, and that we can make it as a CFET. And then the full name for CFET is a complementary field effect transistor technology. So that's a demonstrate coming from the last years. And also, yes, so that's the just let you know that something that starting from the idea, starting from the literature, in the end start to be realized by the industry. And here is just some of the information that's sharing by the industry leading. This is coming from the Mark Liu, the ex-president, CEO of TSMC, and then the Professor Philip Wang. And then just want to mention that this is an application where we have this different deep blue, NIST, Watson, and also alpha, and then come to the chop GPT-4. That's mainly for the chop GPT. So we have this AlphaGo, and then the GPT-3, and then chop GPT. And then this slide just shows that which technology to enable for this application. And then in the future, we still need to, for the next generation, we need to have this nanosheet technology. So let's go through the text here. If the AI revolution is to continue at its current pace, it's going to need even more from the semiconductor industry. Within a decade, it will need a 1 trillion transistors GPU, and that is a GPU with 10 times as many devices as is typical today. So that's expectation. That's for the future GPU. So since we talk about lots of the slide coming from the TSMC iMac, and also it'll be good to see that another industry leading giant in Intel, how do they see their technology development in the next? But the idea is still very similar. In the 22 nanometer, they first to deploy the first FinFET. So that's in the Intel 22 nanometer, and afterwards they are more or less follow the same technology trend that how, or I would not say follow, they are more or less have the same goal like a TSMC did, that they have the enhanced FinFET. And also if you look at their target for the Intel 28 technology, they consider as what they call the ribbon FET. But actually it's the same like the nano sheet, but they just give it a different name. They call this as a ribbon FET. But this is exactly the same like the nano sheet, but they also consider another, they call the power via plus power via. And then the power via is the same like the backside power delivery, or how the TSMC is called the super power rail. It's basically you want to charge it, you want to supply your voltage from the substrate rather from the top, because now you stake too many. If you supply voltage from top, you will lose lots of you have too large voltage drop during the interconnect, and in the end makes it less efficient to apply your voltage. So therefore they decided to apply voltage from the substrate rather than from top. Okay, so that's all. So that's all from the first introductions. So today we'll move on to the next chapter, where we'll start to talk back to the more fundamentals. Okay, so we talk about some of the advanced. We already mentioned a bit about the transistor operation and then the device architecture and the future goals. But we still need to go back to the fundamentals, because of this foundation help us to build up your knowledge for the advanced understanding. So now we will first look at the materials. What actually the available materials that we can have for the semiconductor technology, and then what is inside these materials, especially the crystal structure that we need to understand for this semiconductor material. So that will be the main goal for these chapters. So first of all, by end of this chapter, you should be able to, first one, to understand materials classification. For example, to understand, this is pretty easy, fundamental, and then so it's not that difficult, just need to understand what's the difference between the elemental and then compound semiconductor. So elemental means that silicon and germanium is elemental, is based on the one single species, and then compound semiconductor is based on the 2 different or 3 different elements. And then try to connect the material to the device formation. That's more important because of our goal is not just doing the material analysis. Our goal is not just to understand the crystal orientation. Our goal in the end to understand how we can make it as a device, how the device formation. So therefore, from materials to the device formation, there's a very important concept in between, which is the junctions. So the junction is if we put the 2 materials together, the interface between these 2 materials, that we call the junction, 接面. And then the many miracle physics happening in this junction, in this interface. And many device characteristics are dominated by this interface of the 2 different materials. So that's important to understand how is this junction formations. And later we will start to talk about the crystal structure, where probably if you are coming from the material science background, you probably already knew some of these. For example, the single QB, BCC, FCC, and diamond structure. That's all very basic. We won't spend too much time, but we still need make sure everyone understand. And then we will let you know how the typical we can calculate the outcomes per unit cell and how to interpret the lattice vectors and unit cell. That's all very basic. And also another very important is a Miller index. Miller index is a way to determine the direction, the orientation of the one particular plane in the crystal structure. So we need to let you to understand what does mean for these different vectors here. The Miller index is a very simple, very easy calculate. Many people feel like this is not important, which is not true. In the end, we will show like in the very advanced knowledge in the publication paper, we still need the Miller index to help us to understand the crystal orientation. And also some of the imperfects, especially the crystal imperfections, vacancy, interstitials, substitutional impurity. All these, our crystal is not perfect. We always never be able to fabricate the ideal, the silicon crystal or other semiconductor crystal without any defect. Once we have defect, how do we define this defect? How do we understand this defect? So that's why we need to analyze crystal imperfections. So first of all, if you want to understand the semiconductor device architecture, we need to first to understand how to form a semiconductor device. For sure, when we consider the semiconductor device, it's always we pick up the several semiconductor materials. So we have the materials. For example, first we pick up the P-type semiconductor material, and we have the N-type semiconductor material. So therefore, we have the P, N, and as you already explained, the P means that this is a material full of the hole, has a higher hole concentration. And then the N is a material that has a higher electron concentration. And then we have to consider, if we try to put these two materials side by side with each other, And therefore, now the structure will become like this one, where we have the left hand side as a P, we have a right hand side as a N, and then the only difference is we just pick out these two materials, but now we just do something, try to make sure they were being connected with each other. And once this being connected, for sure that you can imagine that the most difficult and then the miracle part must will be happen in this interface. Therefore, we'll specifically call this interface as a junction. So many of the semiconductor devices actually are the characteristics are mainly determined by this junction. As long as we can understand the junction, then we can understand the device operation. So once we understand the junction, the last one will be device, and which is this one. P, N, and now we consider all as a device. So that's why if you look at the lots of the textbook, not only from Neiman, for every semiconductor textbook, they always starting to talk about materials. They will not just directly jump to the device. They will start to talk about junction. There's always a chapter to describe as a junction between the P and N, the metal on top of semiconductor. That's also another junction. And later, we will start to talk about device. And then I hope this slide can give you as a more overview picture that why we have to learn the material, why we have to learn the junction. Because in the end, our goal is to understand the device. Because if we want to understand the device, we need the knowledge coming from the materials and junctions. And also, I want to spend a little bit time to remind that the PN junction, PN device looks simple, but that's as a very critical structure in our transistor, especially in the MOSFET. So if we can understand the PN junction, PN device, that will highly help us to understand the MOSFET as well. So if you look at the typical structure for the MOSFET, where we have been already shown last week, but now quickly say again, the MOSFET is a transistor considered as a first one. We have as a carrier, which is a substrate. So we consider this as a P-type substrate here. And then we have a source and drain, where we normally has a highly doping in the source and drain region. And later we have this dielectric, which we most often use is SiO2, silicon dioxide. And later we have the gate on top. So we have this one is a source, and this one is a drain. So that's the simple structure for the MOSFET. And the reason I want to show the MOSFET when we talk about the PN junction here, because of many of you, also include me, when I was a student, I always get lost that I don't understand why we have spam. If you look at the chapter contents in the semiconductor textbook, around 70% or 80% is talk about materials, physics, PN junction, PN diode, or metal junction. Only 30% talk about transistor, So I always get confused at why we have to spend so much time to understand p-n junction, because at the moment I didn't understand that I just thought about that the people always call about MOSFET, FinFET, but it looks like a semiconductor physics always talk about the physics, materials, and p-n junction. But the devil is always in the detail, because if you look at the structure for the MOSFET, you will realize that inside this structure, we already have the p-n junction. Because of this structure, that contains in this region, we have the N plus P substrate. So that's as a one p-n junction. On the other hand, if you look at from the drain side, similarly, we have this P and N junction. And also, if you still remember the last week, we talked about very brief for the MOSFET operation is mainly we give the gate bias here, and there's a certain electron accumulated. And then because we have drain bias, so the electron will flow from left to the right. And you can see the electron during the flow, actually the electron will face the two p-n junction. One is here and one is here. So that's why, although MOSFET is very important, but the operation and then the electrical characteristic of a MOSFET is also highly determined by the junction here and here. So that's why in most of the textbooks, they spend a lot of efforts just talk about this basic for p-n junction. But just want to let you know that this, in the end, if you understand p-n junction, that will highly help you to understand the MOSFET. So in the end, the MOSFET, it just combine as a several junction. We have a right-hand side one p-n junction, left-hand side one p-n junction, and we just try to put it as like the Lego. You put a lot of a small block together, that's become MOSFET. But nowadays, what we are doing is just try to understand the principle for each small blocks. Okay, so first one, the elemental, so semiconductor materials, and then what we are talking here is similar like this one. We have a group 4, especially we have this group 4 in the periodic table. We have the silicon, which is no doubt the silicon is the most important one, and then sometimes we also use the germanium here. So the elemental semiconductor, the semiconductor is based on the one kind of species that we call this elemental semiconductor. So the elemental semiconductor that's mainly in the group 4 of the periodic table are composed of the single species of the atoms. For example, the silicon and germanium that's most widely used, especially silicon. So that's a group 4 for the elemental semiconductor. And later, we can consider as what we call the compound semiconductor, where the compound semiconductor are formed So the compound semiconductor are generally formed by using as a group 3 and group 5 elements, and that are combined as 2 elements or 3 elements. That depends on the how we construct our semiconductor material. We can use the 2 elements like like shown me here, gallium arsenide, which is a 2-element semiconductor, or 3 element like the aluminum gallium arsenide. So basically, compound semiconductor is a combination of these groups 3 and 5 together, then we can make it as a compound semiconductor. So in this, one of the very popular that's already used in everyone's mobile phone is a gallium arsenide, which is a combination of the group 3 as a gallium and then the arsenic in the group 5. So that's what we call the gallium arsenide. And also the indium phosphide, that's also very important for the semiconductor. So here is just some more information for the 3-element compound semiconductor. For example, the aluminum gallium arsenide, we can have a different composition for the aluminum and gallium, and then how we usually denote it as a 0. And 0.2, that means 20% of aluminum, and 0.8, that means 80% of the gallium. So that's a typical how you will really found it from the product, from the data sheet, from the literature, that we consider aluminum gallium arsenide with a different composition of aluminum and gallium. And also another very well-known compound semiconductor, for example, the aluminum gallium nitride. Similarly, we can have this 0.20% of aluminum and then 80% of the gallium as well. So the aluminum gallium nitride. So here is some more information for the elemental semiconductor. So for example, the germanium is the first materials that used in the integrated circuit, but unfortunately germanium is a trace material and also has a lot of drawback to use the germanium. First one is a trace material. Second one, germanium has a small band gap. And poor thermal stability. And also very important, the main disadvantage or main drawback for the germanium is that once the germanium oxidation of the germanium, that can be possible to have this what we call the germanium oxide. But the germanium oxide is very unstable. It's soluble in the water. So that's why once we found out silicon, we almost abandoned germanium because there are so many drawbacks if we use the germanium. First one, we don't have very good dielectric. Germanium oxide is very unstable and poor thermal stability. Also, it's a small band gap and the trace material. Although the first IC was demonstrated by using the germanium, and later we found out the silicon, one of the most common elements on Earth. And silicon has a lot of advantage. First one is easy to get it. It's one of the most common elements on Earth. And then the band gap is larger than germanium. And normally, we need to remember the silicon band gap. That's very important. It's a silicon band gap. It's a 1.1 electron volt. And also, one of the most attractive advantage using silicon is silicon dioxide. It's very stable, very good for our insulator because it's very stable, so we can use SiO2 as our dielectric in the MOSFET. So that's why later silicon is almost replaced germanium for the many applications. But also there's one drawback for silicon is indirect bandgap material. That's why we never make it as a silicon as a LED. We will talk about this later, but it's not that very critical drawback here. So right hand side you can see this is the 16 nanometer FinFET that we have the PMOS and NMOS here, and then in this interface, this is where the dielectric is here. So we need to have very stable dielectrics, and therefore silicon and silicon dioxide always has a advantage that the other semiconductor materials are difficult to replace. Okay, so we will stop here and take break, and then we will come back at 11:05.目前是暂定的这样，但是目前还不确定会不会改时间。对，如果你有这个抗生的话，可能就要对，就有可能会改，但是我现在没办法确定，因为要看你的课程的 schedule。对，所以你可能要衡量一下。如果最好，当然我希望是礼拜一早上可以考试。如果课程 schedule 是来得及的话。哦，好。
You can take that one first.
Did you get because of this week is
I just registered, but not sent the sources.
yeah, but now the course is full, so I don't accept anymore. Yeah, because of you are welcome to register next semester. I will also open the courses in next semester.
You want?
Yeah, I will also open the courses in next semester. Okay.
Can I add your course?
Also, the course is full now, so we don't accept it anymore. Yes, okay. You can, but you can register in the next semester. I will also offer the same one.
Sir, in your lab, is there any vacancy for?
No, that's the full also.
Thank you.
I sent you an email
Yes.
regarding the final exam.
Yes.
Have you made any considerations yet?
I cannot make any commitment right now because that's why I list all the courses scheduled in the beginning. I list the course scheduled in the beginning because of they probably has a delay of the class.
Yeah, but I don't see why you can't move one lecture to the evening, like you did for an hour. You had for example, when you were traveling, you have a makeup class at 6 p.m., right?
Yes.
So can you do that one more evening in order to keep the final?
Yes, but it needs to be finished. I think most of students, I think 95% or maybe 90%, they all so it's difficult to address just based on the.
Yeah, but you also said there is 30% international students, right?
Yeah, but the students, they are all okay.
Yeah, most are, but in the end, some of us that want to get home for our families, want to get home to summer job, and there is a reason you have a syllabus, an academic schedule on the NYCU website. It says semester.
But I already list that also the options, right? I didn't say that in my original time schedule, I didn't say the class will be ending where I say that I put that option.
No, of course you're communicating it. Of course you are communicating. This is good. But still, that still doesn't take away from the fact that you are breaking the academic schedule published by NYCU.
No, I don't break it. I don't break. That's the order.
Wait, I will show you.
If you feel like this would be
Maybe I
difficult,
have to drop it, yes, I understand.
Yeah.
Let me just show you so you see.
yeah, if you feel like you'll be trying, yeah,
I will probably be able to take it anyway, but
I put it as a backup because I cannot guarantee if something happens. It's always delay. I think my job is trying to make sure that the course can be delivered in case to everyone. Didn't feel pressure to rush in rather than, of course, if I wish I can finish all the tasks, do it every morning, evening, weekend, I can just ask students to come. That would be another good idea.
yeah, this is the schedule that's published by NYCU.
Yes.
I understand that it's the norm here to somewhere overrun the schedule. I understand that now. But it wasn't, yeah. But usually the final exam should be this week, and then vacation should begin on the Sunday.
I think we never have all the tasks and we finish on exactly the June 8th, the first week. So I would just, I will try my best. I told you, but I cannot make a promise at this moment. Because if I make a promise, if I can make it, you will also get a trouble.
Yeah,
yes. That's why that I want to at the beginning have a tolerance that everyone can adjust. It's just still 2 months, right? I will not just inform you just immediately like next week, right?
I will say one final thing, but I understand it's super. My suggestion is that you move the optional class to the first to make it as
I know, I understand your suggestion. I appreciate your suggestion, but I would say that I cannot make any promise at this moment. That would still be depend on the program.
It just depends on if you're willing to have a double lecture that day or not. It doesn't have to do with progress. What I'm asking is if you can put this on the evening on this day instead. It doesn't have to do with
I would prefer to consider after the because right now it's still too early to make a decision. I would say.
Let's see if I can.
Yes, thank you.
Prof, I have a question. You said that compound semiconductors from 5 material.
Yeah, 3. Many 3 is still there 4, difficult. It's rare to see 5.
Oh, so maybe my question is it possible to combine between 2 elements of 2 and 6? So I found on the internet.
I think it's materials science. I see it's possible, but I'm not sure. Yeah, because nowadays people try to generate all kinds of semiconductors. Some from material science possible, but I'm not sure just whether it can be used as a semiconductor.
I see.
Yeah, it can be the conductor, insulator, or very bizarre material, but just not sure.
A lot of trade-offs.
Yeah.
Okay.
kan inte lova något, kanske inte mer, så kan jag tänka om det. Så där har du den här kraften, eller hur? Varför kan han inte flytta det till veckan innan? Han bara, nej, det går för fort, flytta den. Den svarar på mig, han sa att när han vet hur progress så kan han tänka sig till mitt för att uttala sig. Men han ska bara inte uttala och hålla ett ämne. Så För nu är vi den här stilen här, vi är på sida slide 6:35 då, då börjar vi se. Ja. Man kanske kommer in vidare i tiden, bara för att man kan höra det. Men det är så tråkigt att de inte kan. Men sen är det ju för måndag, så det kan vi bara plocka in ändå. Det är bara tekniskt sett är det ju. Tekniskt sett är det ju 4 ring senare än vad jag hade räknat med. Så det är ju inte jättemycket senare. Hade man åkt hem fredag kväll så åker det måndag kväll istället. Sen är det så att sen veckan kanske inte hade haft någonting, men det är inte kvar igen. Yeah. They're trying to figure out the schedule because he's having the final on the 15th, right? But we haven't really planned for that because the schedule said this will be the final day. But now he's wanting to overshoot the schedule, right? So we have to think if we can adjust our plans and stay until 15th or not.
Men så kommer det frågan. Volym har ju ingenting. Den har vi ju där i maj. Med tidkursen som var avvisad. Men när det skriver
Just det. Det är ju intressant att det blir en tid.
den ligger från där. I natten har vi regler.
Ja, det får vi gå på här.
Kan vi gå
Den här är bara homework. Jag tror att han är ganska samt. Jag vet inte, jag behöver ju precis den här dagen med det där som den här är riktigt. Jag också ser ut som att han kanske tänkte ha en vanlig föreläsning där. Men det här är okej. Typ den då,
jag skulle överchecka.
jag att de vill vara där.
Det är också att ge säkerhet i
Ja, absolut. It's a bit of a mix. It's a bit more one, but it crashes with our schedule. I think it might be. This is the Hanoi one. This one looks like it's NYCU, but when you go to it, it's apparently in Hanoi. Now, the only one here, compound compound.
Okay, so this slide just also another simple review that what we have been having to have from the planar MOSFET. Planar, from the planar where we have this typical MOSFET until the fully deplete SOI. And where we have this insulator below the channel. And then we will have this the advanced version where we have this 3D structure that we call the FinFET. So if you look at the the compound semiconductor that we have already mentioned for the 3-5 material, which is mainly the considered as a 3-5. That, for example, the gallium arsenide. The gallium arsenide has some very important features. For example, the direct band gap. And also the gallium arsenide can have the very unique characteristic that we call as a high electron mobility. And when we talk about gallium arsenide, we have to mention that this is paper published early time 1993. And then this is gallium. The title is a gallium arsenide based heterojunction bipolar transistor for very high performance electronic circuit. And the reason why I have to mention this paper is we are not going to explain the gallium arsenide, but there's one course from this paper probably you should know and you were already aware of. So the second author here is Frank Mao Zhongzhang, where is our previous president for the NYCU, NCTU. So the president, Professor Chen, that he was working on the gallium arsenide in the early time, that starting from 1993. And later the gallium arsenide becomes a key component for our cell phone, mobile phone application, and lots of communication. We need to have the gallium arsenide technology. So this is a paper where he published in the early time 1993. Just let you know that this is also just a kind of the indication that what we are doing for semiconductor, starting from literature, from the paper, from academic, but nowadays if you look at all these very promising, very high performance result, in the end lead to the successful product that help us to have the great life right now. So another very important 3-5 compound semiconductor is a gallium nitride, where gallium nitride has a feature as also has a direct band gap. And because of this direct band gap, and therefore it's very suitable for the light emitting diode, where is LED application. So nowadays if you found the LED component is mainly based on the gallium nitride technology. And gallium nitride also has a unique feature of a high electron mobility. And also the large band gap. And when we talk about the large or small band gap, we always use a silicon band gap as a reference. So silicon has a band gap of 1.1 electron volt. So as long as the band gap larger than silicon, that's what we call the large band gap. For example, the gallium nitride has a 3.4 electron volt. So if we look at the unique property of the large band gap, and combined with a good thermal conductivity, the thermal conductivity means that this material can dissipate the heat very efficient. That's why we call this as a good thermal conductivity. So if you consider gallium nitride as a material that featuring large band gap, good thermal conductivity, that means these materials are promising, ideal for the high temperature application. So why we need the semiconductor for the high temperature? Because of the different environment, we need to make sure that our electronics, our semiconductor can survive in that temperature environment. So now you have to understand that we have a different expected temperature stability for the different level of the electronics. If you look at for the consumer electronics, so the consumer electronics means, like for example, our laptop, our mobile phone, all the electronics surrounding our life. So we normally expect that the temperature stability for this consumer electronics should be up to 125 Celsius degree. Because of our normal life, that 125, that's already is the highest. There's no human can survive beyond 50 Celsius degrees. So the 125 should be enough for the consumer electronics. But there are some applications that would put the temperature spec a bit higher. For example, the automotive electronics. For the case with automotive electronics, we put the even higher temperature spec. We need to make sure that our semiconductor component, our electronics in our EV car, in our automotive car are stable, are thermally stable up to the 200 Celsius degree. Because when we drive in the car, we are not driving inside, we drive outside. We drive in the daily time, we drive in the desert. So we need to make sure that all these components are highly qualified for temperature. So therefore, we set an even higher spec for the automotive applications up to the 200 Celsius degree. And furthermore, there's some application we need to make sure our semiconductor are even more stable with a higher temperature. For example, for the space electronics. For space electronics, we need to make sure that our semiconductor components are stable beyond 300 Celsius degree, because you never know that what would be the space environment that our semiconductor, our electronics that need to operate in. Some of the Mars, the Venus, and some of the Pluto, they might have the environment beyond 300 and even sometimes lower than the minus 200. And these all need to make sure that our semiconductor technology are stable in that environment. For example, if you look at for the NASA. So as you know, NASA for sure is one of the best agency for the space technology. So they are not only launch a satellite, they are not only monitor the situation for the outer space, they also produce hardest, most stable semiconductor technology that enable them for the space exploration. So therefore, they also have the silicon carbide laboratory, and they also work on and develop silicon carbide technology for the space application. And this is because silicon carbide technology, which is also considered a compound semiconductor that has a large band gap, and also silicon carbide feature with a good thermal conductivity. So normally, if you look at the literature, the academic paper published in NASA, they demonstrate silicon carbide semiconductor, even for logic in the silicon carbide, they can successfully operation in the environment beyond 500 Celsius degree. And that's because due to unique properties that are coming from the materials. So, because we talk about the band gap, we talk about small band gap, we talk about the large band gap, and therefore it's very important to understand that what does mean the band gap here. So when we talk about band gap, there's a very unique definition for the band gap. So we have been discussed the band gap for the different material. We talk about silicon. Silicon has 1.1 electron volt for the band gap, which is, and therefore any material who has a larger than the silicon we always call as a large band gap, and any material that has a smaller band gap than the silicon, that's we call the small band gap. And therefore you can see the silicon carbide has a 3.26, and the gallium nitride has a 3.4, and then the diamond has the largest one, has a 6 electron volt, and then germanium only has a 0.67 electron volt. So imagine electron living in the lower flow room, which we consider as a valence band. So here is a valence band. We will talk about the details for the valence band and then the conduction band later, but here just let you know that when we talk about the semiconductor material, we always will look at the band gap, and then if we want to know the definition of band gap, we need to understand the valence band. So if the electron living in the valence band, and to move freely and generate current, they need to jump to the upper flow room, where we call as a conduction band. So the distance between the conduction band and then the valence band, that's what we call the band gap, which is this one. And also that means that the smaller the distance, it's easier for electrons jump. So that means from this schematic we can understand the electrons, if has to jump from the valence band, reach to the conduction band and become as a free electron, and then in the end to generate the current. So therefore the distance is smaller, that means it's getting more easy for electrons jump, and that's also meaning the material conducts electricity more easily. So that's why silicon is easier to conduct electron, because the band gap is not that large. But if you look at the extreme case like the diamond here, so in the diamond we will see that the band gap has a 6 electron volt. So that means that ideally it's very difficult to have the current flow in the diamond, because due to the large band gap. So that's different application for the different implication coming from the meaning of the band gap. So then, once we understand the materials, we understand the key materials features, and then what does mean the band gap. And next one is we have to start to look at what is the junctions here. So as I already said, the junction is mainly to try to gap the understanding between the materials and the device. And then once we put the two different materials side by side together, the junction as a boundary, we need to understand what happens inside the junction. So the junction is a boundary between the two different material. And like for example, if we consider we're going from the paved road to a dirt place, and then therefore condition will change. And therefore, if we consider semiconductor, we have a one materials carrier from one material move to the another material. Also the carrier conditions will change, and that will influence our carrier behaviors. So in semiconductor, junctions affect electron movement and current flow. And they are essential for the device function and control. Because of this, you move from one material to the another material, and therefore this junction will highly influence for the device function and control, and highly influence the carrier, and then in the end will also influence the device characteristic. So why are junctions important is that the semiconductor device use junctions to direct electron flow. So for example, we have a different transistor and then device that we use in our application. For example, we have a diodes. So diodes that the current can be flow in the one direction, and the transistor that will be acts like an electrical switch, and memory that's only rely on the junction behaviors. So to enable these three different kind of a transistor, normally we have four common types of a junction that will be covered in the semiconductor device. We will only see these four different type of junctions. So the first one is the metal-semiconductor junction. And the second one is a PN junction. And then the third one is what we call the heterojunction. And then the heterojunction means that we actually try to put the two different semiconductor material together. So that's basically as a combination of the different semiconductor. And the last one also is very important. We can consider as a junction, which is metal oxide. semiconductor. So that's actually as a MOS structure. So the MOS structure is also considered as a junction. That's why that the MOSFET, if you want to understand MOSFET for sure, you first need to understand the MOS structure, because that will highly influence our MOSFET characteristic. So if you look at no matter what kind of semiconductor device, you will see from now on, also for your research and future, it always combines the combination of these 4 different type of junctions. So that's why that we definitely need to spend certain time trying to understand this, the junction characteristic. And also, if you look at the textbook, they first will talk about the metal semiconductor junction, and they will talk about PN junction and talk about MOS junction, and then start to talk about the transistor. So first, let's just quickly look at for the junction that where we will learn and try to understand from now on and in the future. But now we just give you a quick snapshot that for the different kind of junction. The first one is a metal semiconductor junction. So the metal semiconductor junction is a structure, very simple. Just we have the piece of the semiconductor material, and then on top of the semiconductor material, for sure we were interested in to put as a metal, because the metal is a conductive material. So we always interested in trying to put one conducting material on top of semiconductor. So that's we call as a metal semiconductor junction. So like the contact points between the plug and socket, the metal supplies electrons, and then the metal for sure can supply the electrons, and the semiconductor either can allow the electrons flow or block them. So the metal and semiconductor junction can have the 2 possible functions. One is we can allow the electron flow from the metal to semiconductor, or this junction can block the electrons. So this type of junction is mainly determined whether current can pass through smoothly or not. So if we put a metal on semiconductor, so this is critical that this can determine the current can be flow or can be blocked. And then typically we will often see the metal semiconductor junction in our transistor. For example, this is a typical structure for the MOSFET. And in the previous, when we talk about MOSFET, we only mentioned the substrate, source and drain, dielectric and gate. But actually there is one very important missing, where is normally we need to have the metal put it on top of source and drain region, because we need to make sure that our source and drain can apply voltage, can have the current flow, and therefore this is a place where we have the metal semiconductor junction, and this is a place where we have the metal and semiconductor junction. On the other hand, there's another very important transistor that we call as for here is a gallium nitride HANT, where we won't talk details right now, but this is also another transistor very important. And in this transistor, we also see the metal semiconductor junction in here, the metal and semiconductor junction in here. And this junction plays a critical role to determine the current flow in our transistor. So that's why in most of the learning of the semiconductor, once we finish the quantum physics, the next we will talk is a metal semiconductor junction, because in the end, this is going to be a critical building block for our transistor. And the next one, which is very important, but that's something we have already a brief explained before. It's a p-n junction. So the structure of the p-n junction is also very simple. We have the piece of the material, but right now we still consider the same semiconductor material, just has a different doping. So left hand side we have a p-type, p-type semiconductor, and right hand side we have n-type. And then the interface between p and n is here. This one is a place we call the p-n junction. So p-n junction is the heart of the diodes. Also, the p-n junction can highly determine the MOSFET characteristic, because in the MOSFET where we have been shown, there is a place we have the right hand side close to drain, we have the p-n junction. In the left hand side close to source, we also have the p-n junction. And if you try to look at the inside the p-n junction, for sure later we will talk detail, but one thing we can immediately come to our mind is that this is a region where we have a high electron concentration, and based on the typical physics and chemistry we learn from high school, you have one side as a high concentration. On the other side, you have the zero concentration, and therefore must be the electrons will try to diffuse from high concentration to the low concentration. So that's a diffusion. Right? So diffusion is a basic high school level mechanism. So everyone in here should be aware of the diffusion. As long as you have a high concentration, it's always, as long as the time passes by, the high concentration will try to flow to a low concentration due to the concentration gradient. And that's we call as a diffusion. And similarly, we have a higher hole concentration in the P side. So the higher hole concentration will try to flow from the high concentration region to the low concentration region. So you will see the hole will be flow toward the right. And that's we consider as a hole diffusion. But something's happened. If we only have a diffusion mechanism, you put the P-type or N-type back-to-back connected together. But if you only have a diffusion, ideally, as long as the time passes by, then the N concentration will equally distribute in here and here. The P concentration will equally distribute in here and here. So ideally, once the material being connected, after you wait for 10 minutes, 1 hour, this material become as a same concentration everywhere, because you always have the N and P equally here, N here, P here, P here. So therefore, they should have become the materials that only have the one fixed concentration. But in reality, this thing is not going to happen. So that means there's some very interesting mechanism will try to stop the diffusion happen, and this is something that we will start to talk about during the p-n junction, because it's never will going to be as a material with one kind of a concentration. Okay, and another one here is very important, is the junction between the different semiconductor materials that we call the heterojunction. In the previously, it's the same silicon material but has a different concentration. But now here, what we talk about is two different material. So ideally, we still can try to make the two different material connected with each other. So on the left hand side, we have a semiconductor A. On the right hand side, we have a semiconductor B. So for example, we try to combine as a gallium nitride and then the aluminum gallium nitride. And for example, this is a structure where we have the aluminum gallium nitride and gallium nitride that's being put together. And this is a structure that we call as a gallium nitride hand. And if you talk about the gallium nitride hand, you must have to mention the Professor Mishra from the UC Santa Barbara, where his whole life is working and develop the gallium nitride hand for the power application. He even founded the company who specialized in the gallium nitride power hand transistor. So this interesting structure, in the beginning, it was just a very interesting idea. We put the aluminum gallium nitride grows on top of gallium nitride, but after a decade, this kind of a system device considered as a business, as a product. Nowadays, you can easily to get a gallium nitride product for the high frequency communication for the power application. And this also all beginning coming from the Professor Mishra. And another example of a very successful heterojunction based device is on the right hand side, which is a gallium nitride LED. And the gallium nitride LED is just we put the P type of gallium nitride and N type of gallium nitride. We have a multiple quantum well in between. And because of this unique device, unique heterojunction, so we can start to see the light emitting. And this all has to thank the effort coming from the Professor Amano, which he is a winner for the Nobel Prize because of just due to his effort and then the invention on the LED. Of course, not only him, there's three professors work together to have the great contribution for gallium nitride LED. And then you see for sure that the life nowadays cannot live with the LED, and that has all thanks to the Professor Armanov and his colleagues for his early times development. And then the last one is MOS structure. We have been already explained the MOSFET, and then you already seen inside the MOSFET there's a sandwich structure. There's a structure that we have the semiconductor, oxide, and metal. So this is a structure as a heart of the MOSFET, because inside the MOSFET you can see here is our MOS structure. So normally when we try to understand the MOSFET, we need to spend the effort to understand the metal oxide semiconductor prior to the MOSFET. But nowadays, I think everyone had a little bit understanding about the MOSFET operation. But just let you know that the MOS inside the MOS structure is very critical for the MOSFET. So let's go through the text together. It's like a sandwich, metal on top, semiconductor on the bottom, and insulating oxide layer in the middle. This structure forms the foundation of a commonly used transistor, which can be used to switch current on and off. So the MOS structure considers a heart of the MOSFET, and sometimes we call the MOS structure, and sometimes this also considers a MOS capacitance. So there will be the one dedicated chapter all talk about the MOS capacitors. So finally, with all these 4 junctions, the knowledge of these 4 junctions, that's enough for us to analyze the transistor. But for sure that we just use one slide definitely is not enough, and later each junction will use at least 1 or 2 chapters to explain. And there are also some fundamental series in the semiconductor device that we will use in the future, and also will be explained in this class. The first one is for sure the quantum mechanics. Quantum mechanics here, and then because of quantum mechanics, that can help us to explain many things that we cannot explain based on the Newton physics. So sometimes you don't have to worry about the quantum physics. Quantum mechanics is just a way too complicated. It just as a knowledge to try to help us to explain something that the conventional Newton physics cannot explain. And also, we are engineers. We always as a application related targeted learning. So we will not go through all the detail for the quantum mechanics. If you are from the physics background, probably you will follow the quantum mechanics for the 1 semester, 2 semester. But in this class, we only use 1 class to explain quantum mechanics. We only talk about the most important part that's relevant to semiconductor engineering. So it should be the most not that difficult you have to worry about. So in the quantum mechanics, later we will start to all the series for the the Schrödinger's wave equation, band diagram series, that's all based on the foundation of the quantum mechanics, and later the carrier transport. So bipolar transport equation, when we mean the bipolar, it means that it's an equation that both consider as electrons and holes. And also, we have several different mechanisms. For example, the diffusion, drift, generation, and recombination. And last one is also very important one, is the Poisson equations. This is a critical equation to derive the electric potential distribution based on the charge distributions. These are all the fundamental series that we need for semiconductor. But to be honest, I believe this is not new, completely new for everyone. I think when you're in the high school, in the fresh college, you already learned the modern physics. Inside the modern physics, we already talk about the quantum mechanics. You just didn't know that knowledge can further extend for the semiconductor. And for the carrier transport, when you talk about the diffusion, it's also nothing new. It's just a high school chemistry. You already knew there's one. It's also very intuitive in the life experience. You have one high concentration in one region, definitely where people try to redistribute and make it as an equal. And that's a diffusion. And then drift, it just considers the electric field times the velocity. So this is also nothing new. And Poisson equation, I believe in your general physics, you probably already heard about, or in one of the class you follow from electromagnetics. We already talked about a certain Poisson equation, and then just equation to illustrate between the charge, electric field, and the voltage, and the calculation is also very simple, way simpler than your engineering mathematics. So these three actually become the foundation for semiconductor, and those pieces of knowledge you might already heard before. You just didn't know that this knowledge can extend and consolidate as a semiconductor physics. And in this class, we just use our already known knowledge, but we pick up the most relevant part and consolidate them as the knowledge needed for the semiconductor technologies. Here, just quickly go through. This is also something you probably already knew, that the typical solids, the different material. If you're coming from a material science background, this is something that a piece of cake for you. This is in the material, we all know that there's a different kind of the form of a material. We have amorphous, we have a polycrystalline, we have a single crystal, and the amorphous material has an order or only with a few atomic molecular dimension, and polycrystalline material has a high degree order. And then the single crystal materials has a high degree of order or regular geometry periodicity. So that's a definition between the amorphous, polycrystalline, and single crystal. And you will see this is a schematic for the amorphous, polycrystalline, and also the single crystal. And one thing just want to mention that in the polycrystal, we often see this boundary. And sometimes, most of the time, we call this as a gram boundary. The gram boundary will highly determine the electrical performance of this material, especially in some of the novel material that people are still trying to work on. For example, the ferroelectric material. Ferroelectric material suffering the lots of issue of this grain boundary, and lots of performance highly depends on the grain boundary. So that's just for your information. And we start to move on. How do we understand the lattice? And then to understand lattice, we need to define as several basics unit. And then the first one we define as a unit cells. So unit cell is a small amount of crystal that can be used to reproduce the entire structure, entire crystal. That's just a definition. And then we also define as another one called a primitive cell, which is the smallest unit cell that can be repeated to form the lattice. And in many cases, it's more convenient to use a unit cell. And the relation between the cell and lattice can be characterized by the vector, which is very intuitive. I believe you have been seeing this before. If we have the crystal structure, something like this one, so in this space we have the atoms here, in the corner, so that's a typical lattice in the space here. And how do we define the any point in this space? We just use a vector here. So we can define as this one as a A. So that's a A. And can define this one as a B. And we can define this one as a C. Therefore, any point inside this crystal here R can be represented as a combination of these vectors. So that's also very simple. And since we talk about lattice, so there's some basic lattice that you should know. The first one is that there's several different periodic arrangement of the atom. The periodic arrangement of atom in the crystal is called the lattice. And then the first one here is what we call the simple cubic. So the simple cubic is a structure. Show me here. We have the atoms in each corners, and then each atoms only contribute 1/A. So you have the A atoms in the corner, and each one contribute 1/A for this unit cell, and therefore the number of atoms per unit cell is 1. So that's a very simple calculations. And the next one is also very well known, that we call the body central cubic. That's normally we call as a BCC. Where it's the same, we have the 8 altons in the corner, but the 1 in the center. So therefore, the number of altons here, A times 1 over A plus 1 in the center, and in the end become as a 2. So that will become as a 2. That's what we call a BCC. So the thing so far, the calculations are very simple. And the last one is a face center cubic. Face center cubic, where we have the we have the altons, still 8 altons in the corner, where is A times 1 over A plus 6, because now we have a 6 alton in the face, where is here 1, 2, 3, 4, 5, 6. So we have a 6 in the face, and then each one will only contribute 1 over 2. So in the end, that's become as a 4. So the number alton per unit cell is 4. So that's a very simple calculation. I think so far that the mathematics skill we needed right now still in the junior high level. It even didn't need any what we learned from the university. So that just it's more important to understand rather than to know how to do the calculation. Of course, for the homework, for the exam, we still need to assign some of the calculation, because otherwise it's difficult to do the grading. But still, for the understanding, it's more important. Okay, so this is same like how I already explained. So then we got this is simple QB. So we got the 1 point per cell, and the density will be 1 over A power 3 here. So that will be the number of the density. And this is same. This is just a rub out for the BCC, FCC, and then we have this one that's already shown. This is 2. This is 4. And then this is just a schematic to let you know what is realistic look like for the BCC and FCC. And if we talk about the diamond structure, just will be the 2 FCC sublattice, and then try to combine with along the body diagonal by 1 over 4 QBH. So you can think about just try to shift a little bit of 1 over 4 along the body diagonal, and that will become just diamonds. Okay, I think we will stop here, and then next week we'll start to talk about the Miller index. So if you have any question, just feel free to let me know.